Hey everybody, how's it going? Hope you all enjoyed Ryan Lay's excellent stream. I caught the last bit of it there where you all were working with Pac-Man eating a bok choy or a celery or something. It's kind of cool. How is the connection? Can everybody hear me? Hey there, No Tramish. Good to see you again. I remember you were joining for some of our data viz workshop. Welcome, Silver, Alcid, and Jen. Thanks for joining. It's great to have some of you in the chat. We're going to be going over a little bit of machine learning concepts today, some things that you might even already think you know, but we're going to cover them in some really strong detail to give you some foundation in those concepts. Um, oh, I have pronounced the last name right. Awesome. Glad. And oh, we have another hacker, Shizu. Hi there. Good to see you. So yeah, today our goal is really to dive deep into linear regression, and we're gonna understand a little bit about that method. And people use it all the time, but you want to make sure you're using it appropriately. So with that in mind, we're gonna really make sure that we cover our bases on that. All right, I'm just loading up my stuff from last time. You can see what we did last time. I've just been deleting some of this code. But yeah, we were checking out some data viz um, things. I'm sorry we had to cancel that third part of the data viz. Oh, but yeah, we made some really cool plots. Heat maps, bar charts. If you've never made one of these 3D plots, those are awesome. So definitely check that out, that stream. And yeah, Jensa, I see it in research all the time. Yeah, yeah, linear regression. It's a hugely important topic in research. Um, why don't we go through though, and we'll talk about it today. And then I might get some feedback from all of you on what you want to cover if we do have some extra time. Um, I have some material on a bunch of classification algorithms, also regression algorithms. So yeah, maybe we'll get some feedback if we finish early. But before we even get started, I want to make sure that you can all check in. So here's the check-in link if you don't have it already. It's really important to check in because it helps us see what you're interested in. It also helps you because you can get some points for your Global Hack Week and use those for maybe getting swag. Sometimes we give out swag for these events, and you can use your check-in points to get that. But yeah, let's keep going. Just want to introduce myself because not everybody, of course, is familiar with me. But my name is Stephen. I'm really excited to have you all here and a little bit about me. So I have a background in science, data science, and computer science. Um, I've been working with machine learning for many years now, applying it to solving real world problems. And yeah, it's just really important because it's revolutionizing um, statistics, um, inference, and how we think about data. So we will totally dive into those basics. Today, we're going to learn a little bit about supervised learning and get a little hands-on with linear regression. And by the end of the session, you will actually build your own linear regression model, and we might do some more advanced concepts too. I've been thinking about implementing Vision Transformer, which is was a hit in a previous Global Hack Week, so we might do that too. And that covers our objectives. So let's actually talk a little bit about what is machine learning. So not everybody is familiar with the exact definition. So basically, machine learning is a type of artificial intelligence, okay? And it enables systems to learn and improve from experience without being explicitly programmed. So you are not programming in some instructions on how the machine should explicitly handle some classification, for example. You're going to tell it to optimize according to some cost function, but it will sort of get its own way there based on the cost function that you give it. And there's so many applications for machine learning. So there's facial recognition in photos. There's natural language processing. So there's voice assistants, of course, like Siri, Alexa, and now ChatGPT even has a voice assistant. There's recommendation systems like Netflix, Amazon, and even email spam detection. So you want to filter out some emails that might be spam, and you use an email spam detector, and that's likely built with machine learning. So if anybody has an example that I didn't cover, or maybe something most people don't think about, why don't you put it in the chat? I'd love to see what kinds of examples you all come up with for how machine learning is used in our society. But while I'm waiting for you all to maybe send some comments, let me give some of these types of machine learning. We have several. There's supervised, unsupervised, and reinforcement are the main, or semi-supervised is also another word for reinforcement. Those are the main concepts that we have for machine learning. And why don't we start with supervised? So supervised learning is about teaching the model using labeled data. And each training example is paired with an output label. So yeah, there's some examples here. So we have classification, which was a spam email example we gave. And there's also regression. So let's say you want to predict the price of a house. You could actually use supervised learning to do that. And Ritesh says self-driving cars like Tesla. Yeah, that's another great example. And actually, I learned recently that Tesla uses a lot of transformers to do its computer vision. So that's why I'm thinking we might do some vision transformer too today. But then there's unsupervised learning, which is learning unlabeled data. So this is where you're going to tell the algorithm some data, but you're not going to necessarily label it with the right answer. So in supervised learning, we would teach the model by giving examples like, oh, this is an example of spam. This is an example of not spam, and just go back and forth like that until the model eventually learns. And for the house price prediction, we could easily say, this house costs $400,000. This house costs $200,000, and tell the characteristics, and then the model would learn the costs based on that data. But with unsupervised learning, you're learning unlabeled data, and you're finding inherent patterns and grouping. So some examples could be clustering, where you're trying to look for clusters of data that all share similar features. And then dimensionality reduction too, which is going to be all about reducing the dimensions of data to make it as simple as possible. Okay. So then we also have reinforcement learning, which is, so for example, we have some agent that learns to make decisions by taking actions in an environment to maximize cumulative rewards. So there's some examples here, like game AI and robotics. And so I actually have some example for reinforcement learning too. And I'm thinking we might actually take a poll in the chat. So let me send a poll out because I don't want to just talk about whatever I am interested in. I actually have examples for each of these types of learning. And so let me actually make a little poll. I'm going to say, which type of learning should we focus on for today? And the first option is going to be regression. And so we could do linear regression. The second option is classification. So that would be vision transformers. And the third option is going to be this reinforcement. So I'm going to do, I have an example about wildfire. Okay. So we're going to actually send that out to all of you. I'd love for you all to please vote on your favorite choice. So here's the form, it's in the chat. And let me know which one you'd like to focus on. Let me actually put this up on the screen so that we can all follow along. Yeah, so here's the examples. What type of learning we should focus on today? So linear regression is, we could look at the real dive deep into those details of, how is linear regression working, and what could it be used for? And sometimes people use linear regression wrong. So you want to actually know when it's not appropriate to use linear regression. The classification example I have is with vision transformers. So that's really a lot related to like Tesla, things like that might use vision transformers. And then reinforcement is, I have an example of wildfire management. So it's actually forest management. I'll change that. Well, I won't change it, but it's a forest management game. So you're trying to grow a forest and make it as good as possible, and we will learn some reinforcement algorithm for that. So yeah, go ahead and give those some answers. I have 6 already. So if anybody else wants to vote, just leave it open for one more minute. And yeah, we'll leave it just for one more. All right, we've got 7. I'm gonna go for it. I'm gonna stop sharing because I'm not sure if there's any personal information here. All right, I'm gonna share the result now because it doesn't look like there's any personal information in this. It's just simply the votes anonymized in a pie chart. So actually, it looks like our least popular was linear regression. So I'm glad I didn't go with that. And reinforcement got some votes for sure, but it seems like most of you actually would like to look at the vision transformers. So why don't we do that? And if anyone would like the slides for linear regression or wildfire, just send me a message on LinkedIn. I'll post my LinkedIn too. Okay, last time I posted my LinkedIn, the link didn't work. So you know how, maybe you ask someone for their phone number and they give you a wrong phone number? I don't want you all to think that I'm trying to blow you off. So let me double check and make sure my link works. You don't want to get embarrassed by that. So here's the link to my LinkedIn. If you want one of those slides, feel free to message me. I'm happy to give it to you. But yeah, all right. So we'll talk about vision transformers then. Let me pull up those slides. And yeah, so here they are. Hopefully you all can see. All right, so we'll discuss vision transformers now since we've gone through a little bit of these basics of the three types of machine learning, and you all voted on this image classification. And we're going to implement the vision transformer from scratch, and we will do some theoretical concepts and then some coding exercises. And then the goal is going to be to understand VIT and implement it using the CIFAR 10 dataset. Has anyone heard of the CIFAR 10 dataset? In the chat, let me know. Yeah. Oh, another example of machine learning. I didn't see this, no Tramish, but you said saw it being used in geology, glacier melting, stuff like that. That's awesome. Send that to me if you have some paper or I love to see those kinds of work because actually I do a lot of earth science myself. Um, so definitely send that along if you remember where you saw that. But yeah, does anyone remember where this CIFAR 10 comes from? So it's a really classic one. Chen says, no clue. Yeah, let me actually show you this. It's kind of a bit of history in a way. So, share my tab here. I'm going to look at this link here, and maybe this one too. So here's the CIFAR 10. It's produced by the Canadian Institute for Advanced Research, and they were interested in building a data set that could be used for testing whether algorithms were good at figuring out what an image is. Okay, so for example, there's 60,000 32 by 32 color images in 10 classes, and they're the following. So they have airplanes, cars, birds, cats, deer, dogs, frogs, horses, ships, and trucks. Okay, so each of these has 6,000 examples, and you know the computer algorithm will have to do that. And oh, and look at this. When this data set was created, the students were paid to label all of the images. Isn't that cool? Could you imagine getting paid to label all these images for this state-of-the-art data set? But okay, let's see. Some of these are quite low. Look at this now. There's an algorithm that is actually less than 1% error rate on the CIFAR 10. How cool is that? And you'll see here at the bottom, check this out. An image is worth 16 by 16 words. Transformers for image recognition at scale. So the reason why they call this an image is worth 16 by 16 words is because the original is an image is worth 1,000 words, right? That's the original saying. But here they're saying an image is worth 16 by 16 words, and I'll actually explain the meaning behind that. But for now, just know that this is actually a paper on vision transformers, and they're getting the best result of all, only 0.5% error rate. So we're going to try and replicate that. We're not going to get as good as they did. That would be amazing, but no, we don't really have the time to build an algorithm to replicate theirs. But yeah, let's actually take a look at this data set because it's kind of a funny one, really. So here's the website for it. And check out these images, everybody. Look at this. Can you imagine? I'm not even sure I could do a lot of these. But you guess that this is a dog? You see how blurry they are. But their goal is to really just classify the image. So when they see a new one, say, is this an automobile? Is this a bird? Is this a cat? And think about the case with Tesla too. If you need to know where is a person, right? You don't want to mistake a person walking across the street with a garbage bag flying across the street, right? Because a garbage bag is pretty harmless to your car. And but if a person's walking across the street, you have to stop so you don't hit them and cause a really bad accident. Yeah, no Tramer says, let me know when someone else pays for labeling images. Right? Yeah, that would be kind of a funny job to do. I think a lot of people used to do that job, but it's starting to become less and less common because these algorithms are getting so good at doing it on their own, detecting images, that human labeled data in this way is not really necessary anymore. We kind of have enough of these images. But yeah, for certain cases, I'm sure they still employ human data labelers. And so, interestingly, this person here, does anyone recognize this name here? This person who collected this data set? Someone says Google. Almost. Might have actually worked at Google. But oh yeah, he did work at Google. But so you're correct, actually. That's correct. But what I was going at is he actually won Nobel Prize this year um, for his work on machine learning. So this is a Nobel Prize winning scientist. So maybe someday, if you keep working on some of these things, you could win a Nobel Prize too. Who knows? Um, but yeah, let's keep going, and we'll dive in a little more to this vision transformer thing. So let's keep going, and this is the final solution code. I just put it up here because I want you all to have access in case you're interested in going ahead a little bit, or you need to leave early, or you get a little lost. I'll even put it in the chat, but try not to look too far ahead at this solution while we're going through the project, because I don't want to necessarily spoil the fun at the end, right? So yeah, let's not look at that yet. Okay, so here's our table of contents. We'll start with the intro, do a little bit of understanding transformers, and then do from NLP to computer vision. So we'll talk about how computer vision algorithms actually come from natural language algorithms like ChatGPT, for example. And then setting up the environment, we'll set that up, get everything pre-processed and our data set loaded. And then we'll build a vision transformer from scratch and train it. And then we'll evaluate the model performance and talk a little bit about our next steps. Okay, so as I mentioned, and as you mentioned, Defendant, it's actually Google product here, Vision Transformer. And so we'll check it out. Why don't we look at this blog post about it? I have this GIF in my slides, actually. So we'll take a look at that in a little more detail. But for now, actually, let's focus on it a little bit. So you can imagine having an image, like, for example, our little blurry dog. But that image gets broken into patches. So these patches are having two properties. First, there's the contents of the patch itself. So the patch might have a lot of blue in it. It might have a door in it, for example. So that's the contents of the patch. But there's also the position of the patch relative to the other patches. So you'll notice that we label with numbers here, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's telling the algorithm where each patch exists in reference relative to the other ones. Okay, so then once those patches are ordered out and separated out, they are projected into a linear projection of flattened patches. So basically a giant string of information. And then they can be passed into the transformer encoder. And so um, this is all embedded, all this information, the position, the data itself is embedded in the transformer encoder. And then the algorithm operates from there on a lot like a normal transformer, which would take a string of words. So you can just think of it like a normal transformer, but it's actually going to take the image as a word almost. Okay, so let's see. I don't know if there's anything else I wanted to show you from this website. It's a really cool one. Oh, this is a good one to look at. So this algorithm here, ResNet, is a CNN algorithm. Has anybody heard of CNN algorithms? I'll type that in the chat. So this is the CNN algorithm versus the VIT algorithm. And you can see that this plot shows how much accuracy you get from the algorithm versus training time. So most people know that scaling is very important with machine learning. So the more computing you use, computing resources you use to train the model, the better the accuracy becomes. You can see that they only achieve these really high accuracies after so much training. We're probably going to achieve something more like this bottom end here, 94% or so. But if you were to code up an algorithm and train it for so long, you could get much higher. But yeah, as Consistent Coder says, convolution neural network. So it's a little bit different than transformer. It's going to be more based on applying a kernel to an image to extract the features, the most important features. But this plot is showing that the transformer actually is better performing in many cases. So that's another interesting thing from here. And I wanted to also show this one from their work, which is indicating how the different VIT models compare to one another. So they're using B, L, and H to refer to, let's see, I forget exactly what they refer to, but I think it's high resolution, low resolution. Okay, it doesn't quite say here, but I think H refers to an algorithm that is let's see here. I think they're just the amount of layers that they have in the algorithm. So H would be something that has many layers and is more complex model. Of course, it'll require a lot more training time. And then L would be something lower resolution. I think that's what it is. But I do know that these divided by numbers here are the patch size. So that's how big the patches are that you divide the image into. And so you'll remember that castle we saw was divided into 9, 3 by 3. But if you divide into more and more images, so if those patch sizes are smaller and smaller, like in this case, VITH 14 is really small patch size, only 14. That's going to get you a really much better result. So the patch size is also very important for getting a good accuracy. And then they show our data set here, SciFAR 10. You can see there's a 99.5% accuracy. So yeah, just kind of a really cool concept here. And we're now going to talk about how transformers revolutionized NLP. So there is what is called NLP, natural language processing, and you all remember when ChatGPT came out. That's a huge breakthrough. And what it's doing is using this transformer algorithm, and each word, instead of patches, those would be words, and each word is considered in its position relative to the other words and the content of the word. And it applies what they call a self-attention mechanism, which allows the models to weigh importance of different parts of an input sequence independently. So that means that every word and its relationship with the other words can be modeled independently. And additionally, it's processing all of these elements simultaneously. So it's considering the entire sentence or the entire image in our case, all at the same time. It's not considering them one by one like an RNN would, which is another type of algorithm, the recurrent neural network. It's similar to CNN as you would have for images. But basically, the RNN will process the sequence in order, so considering each word as it goes. And then there's a few key components of transformers I wanted to also mention. So, for instance, there's self-attention, which enables the model to focus on relevant parts of the input. Okay. And then there's positional encoding, which adds information about the order of the input elements. So that's what I'm talking about when I say that each patch could have some number, and in that way their order is marked by in the data. And then the feed-forward neural network processes the output of the self-attention mechanism. So it's saying, okay, look at the self-attention, see how each of the parts of the input are relevant or not, and then process that in some output. So again, we had this. This is just part of the algorithm. So unlike text, you have to actually project these out into something like a sentence, and then it gets flattened up, and that's what is input into a VIT. So let's actually take a quick quiz here, because I want to make sure that you all are paying attention. And can anyone tell me, what was the original domain of the transformer model? What was it used for first? Anybody remember in the chat? Jen says B or A. Yes, so it's actually going to be B. Now, A did come later. That would be with the vision transformer, but originally they're using the transformer for NLP, like things like ChatGPT, and so things like that. And another question for you. What is the primary function of the self-attention mechanism in transformers? Okay. Anybody know the answer to this one? We talked about it a little bit. Getting a few folks telling me B, defendant, Jen, Neelish, all saying B. And yeah, you're all right. It's B. So the self-attention mechanism focuses us on different parts of the input sequence. And we're actually going to take a deep dive into that now. So I don't want to just tell you, oh, this is what it does, but I actually want to show you. Okay, so here is the self-attention mechanism applied to a sentence. All right, and it's just to give you an idea of what this looks like. Each element in the sequence, so in other words, each word in the sentence, can attend to every other element. So look at this. Look at this word here. It. Oh no, Tramish. Sorry to see you go. I hope you feel better. Yes, I was actually having some sickness yesterday. I wasn't feeling very good. So everyone be careful out there. But yes, we have some context, um, and, uh, and that context is going to be weighted by each word. So, for example, it. What do you think it is most related to in this sentence? The animal didn't cross the street because it was too tired. Okay, and so there's going to be some idea of the attention towards it. So look at this orange shading here. Orange shading is going to indicate the context for it. And so the animal is really highlighted here. And that's because it is the pronoun that actually refers to the animal. And then there's also in the green, this is the other dimension upon which it could be related. It's tired. Okay, so you see that green is showing um, that the animal is tired. So that's very key information. Yeah, exactly. A McSizzle bunny, as you said, it would be the animal. So that would be the most important feature. And you see that with the orange shading. And so let's talk now a little bit about the transformer architecture, which is basically what we call an encoder-decoder structure. So the encoder processes the input sequence, which, as we established, it's going to be this linear projection of these flattened patches of the image. And then it generates a representation, while the decoder uses this representation to generate the output sequence. So that encoder might be composed of many layers, and each one would have some self-attention. Calculate the intention between each word, and then feed that forward to the next one, just extracting what are the most important key aspects, and then it'll go through to the next one and next one and next one, and that's, the more of those layers you have, presumably the better it would then be. And so let's now talk about positional encoding, which is another concept in the transformers. So we discussed this a little bit, but transformers process inputs in parallel, and so they lack some built-in sense of order. So to give that order to it, we're going to use positional encoding to tell it about which patch goes where. So we'll add a unique vector to each input element based on its position in the sequence. And so that's really key for vision transformers. And I'll also talk about multi-head attention, which is another aspect of transformers. So this allows the model to focus on different parts of the input simultaneously. You remember we were saying that it's going to look at every part of the input simultaneously, and each head will compute this attention independently and combine them to form the final output. So that's, each in this sentence that we had, all those words would have their own head, right? So let's answer some quiz questions now. What is the purpose of positional encoding in transformers? Have some options for you. It might be to speed up the training. It might be to provide some information about the order of the sequence. It might be to normalize the data, a very important thing in machine learning, or it might be to reduce the number of parameters. So which one is positional encoding accomplishing? Okay, a lot of people saying B. And yes, it is. So you will provide some information about the sequence order. And another question for you. How does the multi-head attention improve the transformer's performance? So remember, multi-head attention was where we were having, you know, ability to look at the attention in all of these different inputs. And compute them together. Yeah, so defendant says A, that's right. So it's actually going to be A. Okay. And so now that we've done a little bit of our homework on transformers, you all have been great students on this. I think we're ready to go to computer vision. So let's adapt this transformer architecture to handle images. And, the patches are flattened, as we said, and sort of converted in. And I want to also mention the difference between CNNs and VITs, which is something I talked about earlier. But remember that VITs were actually a little bit better than the CNNs. And they process spatial hierarchies in images, whereas VITs treat images as sequences. So what the CNN does is it uses a filter to detect a local pattern. So it'll kind of almost shade the region where it thinks it gets the most information from. Shade in the sense of, it'll like highlight that region in its mind, in its mind's eye, and then use the data from that region to detect some local pattern. But the VITs can actually look across the whole image, not just using some filter, to capture how every part relates to every other part. So why do VITs work? Well, there's a few reasons. They excel in capturing long-range dependencies and some of the contextual information that are really important for understanding some of these complex visual scenes, and their ability to really process the entire image as a sequence lets them do this outperforming of the CNNs. And so there's that slide I showed you earlier where we had an example of VIT versus state of the art. Many of these state of the arts are actually coming through the CNN algorithm. So here's another quiz for you. How do these vision transformers process the images differently than CNNs? And after this quiz, we'll do some practice. So get ready for that too. All right, a couple people saying C, and excellent work. Someone coming in late, actually. Beware the Jabberwocky. But you're actually right. So good job. Even you came in late, you still got the right answer. And one last question for all of you. I know you're all probably tired of doing these quizzes now. It's been a long amount of quizzes, but what is one advantage of the VITs over the CNNs? Do they require less data to train? Or maybe they have fewer parameters. That'd be nice. So I'll tell you, actually, for A, they actually require more data to train than CNN typically. And they actually probably have more parameters. But Yes, as the defendant says. D, they capture long-range dependencies more effectively because they can consider the whole entire input sequence all at once. So that's a really big difference. So let's actually get some practice through. I mean, after all, we're all here together, so we might as well try it. And I want to start by directing you to this Google Colab link. So it's a great product for doing machine learning. And I have my own Google Colab. You can get yours too. You might need to do a free trial if you want to run this model, but you can do all the coding, and then just let me run this. But I'm not sure. You might be able to run it on your own. Yeah, Google Colab's always changing their subscription info. I'm going to look up actually what are the free Google Colab GPUs. It's like you can use T4 GPU. But yeah, let's actually navigate into this. And I'm just going to make a new notebook here. Push new notebook. And the first thing we're going to do, I'll just give it a name. Vision Transformer Practice. But the first thing we're going to do is install some of these really important libraries that we need to get this this off the ground. So we need to install Torch, Torch Vision, Tim, and Matplotlib. So these are some of the things we'll need for today. And the way you can do that in Google Colab is by actually typing at the top here. So you type pip install Torch, Torch Vision, Tim, Matplotlib, and just hit run here. Can take a while actually. Let's see what runtime I'm using. Okay, looks like I'm using CPU. I'm gonna try to use T4 GPU. You should be able to, I think, use the GPU. Even with a free version of Colab. Let me know if you're not able to. For whatever reason, you might not have access to a GPU, but you'll definitely want it for this transformer thing. Okay, looks like everything is installed, which is great. And why don't we now check out these import statements? So I have a bunch of imports that we're going to do. And so I'll start with Torch. So Torch is going to give us some of these really key machine learning modules. So NN gives us some of these layers, like the linear layers that we'll use to make our feed forward. It has some transforms, and this is not the same thing as transformer. Transforms tells us a little bit about how the data could be normalized, for example, which is really important for machine learning. I'll come back to that. And then Torch Vision datasets, that's where we'll access our CFAR 10. Neelish says, do I need to change the runtime to T4 GPU? I think you do. Yes, I would do that. I think you will need to do that. But yeah, then the other one we have are the data loader, which is another Torch utility, and it's used to basically, um, you know, load up these images for us to train. And then there's also these this TIM. TIM is where we're going to get some pre-trained transformers. So we're actually gonna use some pre-trained VIT. And then matplotlib and datetime we'll use too. Someone says Torch is module. Yes, so Torch is a really common machine learning module, and it lets you basically you make deep neural networks, things like that. That's why we have Torch NN. So we're basically going to use Torch to connect a bunch of VITs together. But let's actually implement this in our code. So let me make this a little bit smaller so that I can actually see here. Because I want to copy the code correctly from the slides. But yeah, if you all ever get stuck, remember we have that example from before. So you can always use that code example, but I pasted it in the chat actually, in case you get lost. But yeah, we'll import Torch. Make this even a little bit smaller. Import Torch as .nn as nn. This is just to make things a little bit easier. Got our data sets in. Optim. Now, torch.optim, has anybody ever heard of an optimizer? So optimizer will basically be really important for minimizing the cost function of the machine learning algorithm. So that will help us get as close to the right answer as possible when it comes to classifying these images. And of course, our data loader, our TIM. I have to import datetime here. Guess to do times and things like that. And then matplotlib. So let's run this code and then we'll just import a lot of these libraries in. All right. So let's go ahead and check out what's next. The next thing we're going to do is this CIFAR 10 data set. And we already talked about it a little bit. We have 60,000 images to load. It's a lot of images, but yeah, we'll get it done. So here's the code for doing that. And remember that code, I also gave you the solution, so you can copy it from there too. But I'm just gonna leave it up in my Google Colab so that you can follow along as I type it. Okay. So the first thing to type is transform equals transforms.compose. So this is going to help us make a new transformation that we're going to apply to our CIFAR data sets. One of the key things we have to do, remember our original data is 32 by 32, but the vision transformer model that we're going to use is actually trained to be 244 by 244. So we can use transforms.resize to resize to 224 by 224. All right. And then we're going to do transforms.toTensor. So when we do that, we're transforming these images into essentially a multi-dimensional array of numbers. So making the data numbers in a way. And then we can normalize it. So I actually didn't choose this normalization. I just wrote this because I just defaulted that in Gemini, but I picked out these numbers especially for this task. And so what these numbers are doing is normalizing each of the dimensions to some mean and standard deviation, so that all the colors, all of the colors in the image are all kind of those numbers that we had are not going to be some huge range. And this is really important for machine learning algorithms. For whatever reason, honestly, it's not always known why, but yes. All right, so let's keep going here. We'll run this code. Oh, just a little issue here because it should be capital T, toTensor. And then our data set, we'll say, we'll use Scifar 10. So I have all of these downloads here. And notice we're going to apply our transform to this data set. Okay, so let's just try to load that up. You can see it has nicely extracted that out, downloaded that out, and it worked. It went ahead and effectively got that working. So now let's do a train size and test size. So a lot of you might not be familiar with this, but does anyone know what train size and test size represent? And we're actually going to make 3 different kinds, or I'll just call them train size and validation. I guess I just named them val size, training and validation. Does anybody know? I think I already imported random split, or no, I didn't. So that's good. So let's just run this. Anybody know what that is? Yeah, someone says you're cutting up the data into 2 sets, training and test. And Jen says training data, that's right. So essentially what you're doing is you want to make sure that your algorithm gets trained properly. So you put most of the images in the training. So that's why we say train size is 80% of the data set, right? But then the other one is going to be the validation. So for that validation, you want to make sure that the training data set is appropriate we did not miss anything. So you're going to validate the model to make sure that it works even on data that it's never seen. So that's why we have this validation, which is providing a store of images that you could then test the model on at the end, right? So, all right, let's keep going here. We're going to do some loaders. So we have train loader, and remember I had this imported data loader here, and it requires some of these variables to be defined. I even put num workers, which just tells the algorithm how much it can devote to these loaders at 4, but you guess you don't need that really. But the data loaders is now going to load these training data sets and validation data sets in. And it loads them in batches. So, there's 60,000 images. So we don't want to show them all to the model at once. We'll show them in batches of 64. And the model then can tweak itself and jiggle its parameters up a little bit each time, and see another 64. And that actually tends to work really well for training machine learning models. So that sort of covers the, oops, that's reinforcement. That's from last time. That covers that. And we'll go back to this setting up the CIFAR 10 data set. And yeah, let's keep going with pre-processing and data augmentation. Yeah. And Anushka said, very good point. So train size is the amount of data that we'll be using for training. And then the test and validation is the remaining data that we'll use to test the model. Yeah, because we want to make sure that our model can work on stuff that it's never seen before, right? We want to make sure that it doesn't just work on things that it's already seen before. So thank you for that explanation. And so data processing is really important. It's a critical step in machine learning for resizing, normalizing, and augmenting data. And it artificially increases the diversity of the training data set. So it can improve that model robustness by removing some of the tendencies of the model to overfit. And I actually have a great image of what overfitting is. Oh, a couple of questions. Is there any situation where you would use 90% training and 10% testing? Yes, you could do that if you have a lot of data. You don't need as large of a testing data set. So you could do that if you have a large amount of data. But if you have a small amount of data, you really want to have a large testing because you want to make sure the data is not overfitting. And I'll show you, I'm actually going to show a little slide that I have. Let's see here. Oh, it was in here somewhere. Oh, so many. I have so many slides everywhere. Okay, slide 28 on this deck. Okay, here's the slide. So underfitting versus overfitting. You can see, imagine this line is your model, and imagine that the blue and the orange are two different types of images. Well, if you underfit the data, that means that the data has not seen enough training data in order to actually appropriately calibrate the model. And then so that's why, it makes this straight line, but it actually misses a lot of these orange points and even puts some blue points on the side of the orange points. And then if the training is overfitting, that means that the model has gotten so specific that it's really not doing any good job of making a generalization. So it's saying that any point in this little loop here, you can see these little loops that it's created. says, oh, if the point's in this loop, it's an orange point or a blue point. But is that really meaningful? Because if you imagine there are some points that are so close by, they're not included in that loop, and yet they're classified differently. So that overfitted model might be way too specific. So that's the sort of reason why we do this process of validating the data to make sure that we're not in either of those cases. And so then again says, does the data have to come from the same source to test it? And actually, it's common in machine learning to do that for your first test, but increasingly people are turning to out of sample validations. So you're actually taking the new data set, apply that to your model, one that is totally different, and see if it still holds. So that is a really good way to check. So those are some really good questions. And data augmentation is a way of artificially increasing the diversity of the data, training data, to make sure that the model sees even more stuff. And I'm going to show you how we do that. So there's plenty of ways to augment the data. And just because we don't always have so much data to make sure that the model is perfectly fit, so we'll look into that and some of these techniques, and they're pretty simple techniques, honestly. So why don't we actually go up to our train, where we did this transform, and I'm going to actually augment these transform functions. So I'm going to make a transform for train. And it's going to be sort of special in the sense that, yeah, we start off with this resize, just like we did before. But I'm going to add a few ideas here. So here's some ideas. First, let's do a horizontal flip of the data. So it could randomly flip that data. So the dog might be upside down. And what that means is that the model thinks it's seeing two different images. And so it could learn from both of the dogs, the dog and the upside down dog. And then the random rotation is just sort of turning the image a little bit in one direction or the other. And then here's the tensor again, like we did before. And we have to do the normalize too, just like we did before. And then the validation transform val, we're not going to do any of this augmentation, because the augmentation is really only for training. We don't need it for any validation. So we'll just leave that out for the validation transform. But now when we want to do this train versus test, we can actually separate these out. So I'm going to do train data set. And we're going to apply the transform train. And we'll do validation data set. And we'll just apply that there. And so now the training and the testing data are being transformed differently. So we'll run this code. A little error. Oh, forgot to run the cell above, which defines all these transforms. Wonder what the issue is for this one. Oh, always going to see a typo when you do Global Hack Week, right? That's just how we roll in the hackathon community. Okay. Now we can run this. Awesome. So our training data set ran just fine. Just make sure it's there. Yep. So we do have about 50,000 data points here. Okay. So let's do a couple of quiz questions now. Remember, I was telling you about data augmentation. What's the primary purpose of data augmentation? Does anybody in the chat know? All right, we have some people saying D. So let's see. Yep, that's right. Artificially increase the size of the training data. And it's important to do that because the more data you have, the less of a risk you have of these happening, underfitting and overfitting. Okay. So let's keep going here. What's one of the common data augmentation techniques that are used for images? Does anybody remember one of the ones that we did? We actually did two kinds in our Python code, but only one of them is here in this quiz. All right, some people saying A. Let's check. Yes, random cropping is an example. I guess actually we didn't do any of these today. I thought we did one of them, but we did not. So let's now load and fine tune a vision transformer. And we're going to make a new class here called VIT model in order to implement that. So let's go back to our code. And you're going to define a class. So that class is going to be VIT model. And it's going to take an NNN module as an argument. And we'll see what that is very soon. But I wanted to say first some init function. And init always runs when you make a new instance of this class. So we can give it self and even a variable num classes. So that would just be the number of classes. And then we'll give a super VIT model self.init. So it's going to inherit all of the class, all of the important things that come from the nn.module from Torch. But we're going to add some new things. And so the first thing we're going to add is a model attribute to this VIT model object, and it's going to be tim.create model. So we're going to create this new model, and it's based on a pre-trained VIT, which was created by the Google Brain team. And so it's pre-trained on a few images. Of course, we'll have to train it for our SciFAR 10 data set, but it's already pre-trained to make the parameters a little bit more friendly to us. And then we'll do a head on this model, which is going to be linear. So remember, we need to have multi-tension head. And we'll make a forward path too. So the forward path just returns the model again. So we'll pass it to the next layer. So this is how the model works. It's just going to pass on over and over again into this VIT and then create a linear connecting head, which will connect to the next layer and so on and so on. Okay. And so there's a few things we'll need to train the vision transformer. we're going to need to define some of these variables. And one of them is the batch size. So you'll remember with that data loader thing, we gave batch size of 64. So that's one of the things that can be defined. And then we also had this LR, which is the learning rate. And you might have heard of this before, but the learning rate is going to be, telling the model how fast it should converge to a solution. So think of it this way. Imagine you are in school and you're taking a test. And in one case, the test is going to ask you a question and you have 30 minutes to solve it. But in the other case, the test is asking you that very same question, but it's only going to give you 1 minute to solve it. Well, in the first case, your brain can afford to think about it a little bit, try out some different ideas, sit with the problem, let some things come to you. But in the second case, you really have to just give your best guess right off the bat and really start to think about that quickly. So learning rate will tell the model, can it afford to tweak a lot of its ideas and weights and parameters, or should it just immediately settle on some way to solve the problem and stick with that? So learning rate is really important parameter. N epochs is going to tell you the number of epochs. So epochs are the number of times that the model will see the training data. So it could see it once only, or you could show it many times. And think about this like flashcards. If you look at your flashcard deck once, that's not going to be that much, right? But if you look at it 6 times, eventually you'll get there. And then number of classes is telling it how many categories the data set has. And CIFAR 10 has 10. So, or Cipher 10, I guess you would call it. So here's the training loop. I have the link to the code again. I don't want you to have to, see that all again. But I'm gonna show my code. And so there's first, I'll copy and paste some of this from the example, but the first thing we're going to do is initialize the model, its loss function, and define its loss function and define its optimizer. So to begin, we actually need to define the device that we're going to use. So you're welcome to use that CPU, but I highly recommend you switch to T4 if you can. I think you should be able to, even if you don't have a subscription to Google Colab, but that'll make it a little bit faster to run. And then we'll have a new model, which will be the VIT model object. We need to pass a number of classes. And if you remember in the init function, we put number of classes as part of our linear layer here. So that's what's going to tell us the output there. And then we have the criterion. So that's the loss function that we use. And the loss function is going to tell us how bad are we doing at classifying the training data. And we want to make that number as good as possible so that the model gets really accurate. And the optimizer is going to help the model get closer to that cost function. So it'll take the parameters of the model and optimize them using this learning rate. So to converge on the solution. So we're just going to run that first. Oh, got to run my class definition. Now we can run this. Oh, should define some of these things. Let's see, what did we have? We had batch size. We had LR was 1E-64. We had number of epochs. Remember, you can adjust these things. If you increase the number of epochs, it might look a little bit better. Change the learning rate to change your answer. But now we initialize this model and the loss function and some of these things. So it's now worked, and it downloaded 364 megabytes. That's the size of this base VIT model. Pretty small, honestly, for what it's able to do. But the next step is going to be to make a training and validation loop. So I'll start by just having some empty lists here to capture the training loss, the validation loss, and the validation accuracies. And so the loss, remember, is according to this cross entropy function. So it's just going to calculate how many of those images are we misclassifying and try and minimize that as much as possible. And then we're going to create a training loop. Remember, we want to train 10 times for the 10 epochs that we have. And we'll just run this function, model.train. And that's built in because train is one of those modules that comes with the nn.module here. So we can use it. And it's going to, we'll start off with train loss of 0. But now for each input and each label in the training data loader, so the training data loader, an input would be the image, for example, and the label could be dog or cat or anything. There'll be 0s through 10, the numbers. But we'll have some inputs and some labels. So we're going to put those into the device. I'm actually going to just copy this from the code solution to save a little bit of time. But then the optimizer will work using gradient descent. And the outputs will be saved. And you just take the outputs of the model and compare them to the labels, which are the true answer. So this is the prediction, this is the true answer, and compute the loss. Okay. And so then here we're just adjusting the model's parameters to accommodate, to improve its performance. And then we add the loss that was computed to the training loss, so we can see how that training loss is changing over time. And I'll append the training loss here to the training losses list. And now it's time to put some eval code. So eval, remember, this is our validation step. So we want to validate the model using data that it's not seen in the training process. So each time we go through a new epoch, we do model.eval, which prints some of these, which basically perform some of these evaluation tasks on the model. And then validation loss, just like we defined training loss. And I'm going to put two variables, a correct and a total. And so the correct is telling how many of the predictions were correct, and the total is just telling us the total number of predictions made in the validation step. So we'll just go through all of these inputs and validation and labels in the validation data set, and we just send them to the device and compute exactly like we did with the training. But we actually want to tell how many we got right. So we're going to use the predicted to store the predictions, and then add to total the total number of data seen, and add to correct the predicted equals labels sum. So that's how many of these predictions matched the value of the label correctly. So then we can just simply have some validation losses here. And validation accuracies. All right, so that's just going to tell us the loss and also the accuracy, because I want to know how many of the total number of things that they saw, how many of them did they get correct? And we'll just print out all that information so that we can see it. And print it out every epoch. Okay. So let's save the model just for fun. Why not? We worked hard on it, so we should save it. And then I'm going to plot a few things. So we'll plot the training and validation loss, certainly. But we'll also plot the validation accuracy. All right. And so that'll help us just see how we're doing. And I want to show you all just how long this could take with your T4, unfortunately. So let me show you. I've been running this ever since we began this workshop. And here's the first epoch that finished. So it says epoch 1 out of 10. So it's all the training data once, and then the training loss, 0.2, it's basically telling you how frequently the model messed up. And the validation loss is a little bit lower, actually, which is a good sign. And the validation accuracy is showing, again, what percentage did we get that correct? And so great news, we actually start off with 96% accuracy here. So that's great to see. I actually want to try running this, though, with one of my higher power GPUs. And for the record, if you want to just leave this running, to do 10, it probably will take about, maybe it could take 10 hours, honestly. But just try to do that. You could run it overnight maybe on your computer and come back in the morning and see the result. But I'm going to try another runtime type. I'm going to try an A100, which is one of the best GPUs you can get on Colab. And I'm just going to run this all again, this whole entire library here. So let's see, follow our cursor and see where it's going. It goes, importing everything. Downloading our model for us. How kind. And it shouldn't really take that long. How's everybody doing with this? Was anybody able to get this code to work? I bet you're still waiting for the results. But as long as it's working, you're getting some output, you know that the code is running correctly. And Beware the Jabberwocky said, I'm not sure if you mentioned this, but can the VIT training be used to train voice recognition? I bet it can, yeah. A transformer certainly can. VIT, you might be able to look at an image of a waveform and see if that waveform looks like someone's voice. But you can definitely use transformer because you think about it, it's just a sequence of sounds in order. So that's a really good idea. Why don't you, see if you can try that. Why not? But yeah, man, this is really taking a long time, isn't it? Let's see, where are we? We're calculating the train loss. Yawn. I wonder if I have any example to show you with the plot and everything. Yeah, I don't think I do. That would be certainly would have been a good thing to do, right? Have some final example for you. Let's see here. Yeah, I don't think so. So we'll just have to wait for it to go through. Another person says, did the save model code go and below go in the same code blocking collab as the training and validation loop, or was it a new code block? Oh, good question. So the save, let's see, where was the save? Oh, it wasn't in this. Oh, yeah, it was. So the save goes in its own thing. You only need to save once at the end. Yeah, certainly some activity going on here. That's good, at least. Maybe we'll get some results. Okay, so wait till the training code finishes and then press play on the save portion. Yes, exactly. So that'll save your model. And then once the model's saved, we don't have to go through this arduous process of training it. Yeah, which could take hours, honestly. You can just load it up and start predicting images. So the prediction part is super fast in traditional transformer architecture. Starting to actually get some models like the GPT-o1 that do some inference um, scaling. So they're actually going to try to do some of that at test time. So it's not as fast, but it's still pretty much the most of the training happens at the, or most of the computing happens at the training period. So here's what I'll say to all of you. Why don't you try to make this run on your own? I'm going to try on my computer, certainly. And we'll just see how long it takes for our models to run. And how about in next time, which is only in a couple hours, actually, we will go ahead and see the result. Oh, look at that. Already got what I got last time. Oh, not as good as the first run, but it's going to take 10 more. So we'll just wait for these to happen offline. Okay. And the next workshop, let's see what it is. Got to make sure we don't forget. Let's see here. It's going to be another one with Ryan Lay at um, at 5 p.m. Eastern Time. Let's give a shout out to Ryan Lay. So, part 2. It's customizing your website with p5.js, part 2. Okay, Sizzle Bunny says, how are you checking the result in the Colab UI? So in the Colab UI, I can see here, actually, the result, because I asked it to print out. So here's my print statement. It runs every validation step, and it tells me how the model's doing. And so I just scroll down to the bottom, check the result, and yeah, we'll look at this in the next workshop. I think we'll also do a little bit of more classification algorithms in the next one. We might do some k-means, k nearest neighbors algorithms and things like that. But yeah, check out Ryan Lay's stream next. And yeah, it was great to have you all here. I'll be back at 7 p.m. Eastern time. And here's the link to the event. Okay, yeah. So the reason it's not showing is because it's going to take a really long time. So it could probably, you don't have this A100 GPU unless you want to buy the subscription. So you're using a T4, it should say T4 up here. And that's going to take a lot longer. It might take about an hour for it to run in Epic. So just remember, it will probably take about 10 hours for it to run fully. But mine will finish by the next workshop. So I will finish it on my own and let you know. Yeah, no problem. But yeah, part 2 of mine is at 7 p.m. Eastern time, so that's going to be pretty soon. And I'll see you all then. Take care.